In this third part of the course, we'll be discussing spatial information aggregation. This is a common problem in geosciences and geology in particular, where people provide several sources of information. We call that layers of information, and they need to combine these layers of information into some kind of a decision variable, or possibly some potential variable, or a sort of total informative variable. So this could be part of GIS software, but underlying all these softwares are, of course, particular statistical methods. And so getting some understanding in those methods is part of this, the goal of this set of lectures. The first lecture will talk about some important examples of this. Those examples, there are many papers, anything with susceptibility or potential analysis, whether it is for geothermal, mineral, and landslides. Many papers like this. I just list a few, and there's also the ones I will be delving up some examples from. So the idea of aggregation of information in general is an important one and occurs in many situations. So here's a simple case. Let's say we're looking to hire somebody, these famous people here, and we ask them for an interview, and there are 3 evaluators, and these evaluators will be testing those or scoring those in 4 categories. First category is teaching abilities, second is research impact, and say the third is fit to the particular department or school where they would be having a position. And then they will be asked to provide an overall score. So the question is, who would you hire? And then the question is, could be, how would you then aggregate all these scores into, say, some kind of ranking of these candidates in terms of your criteria by which this is, and this is here this number of criteria. So the usual way of doing, let's say, is just average everything, and of course averaging comes with a regression to the mean. That also means that good candidates are suddenly not looking as good, and poorer candidates are looking much better. And so the question is, how would we do this in a very different fashion? And that's the issue. That is basically the top of information aggregation. How do we aggregate all this information, and what are kind of criteria that we will be looking at? Well, a number of criteria could be the fact that there's some dependency between these criteria, in particular the overall criteria, or there may be some redundancy in the information that they provide, or there may be some redundancy in the information provided by the evaluator. Evaluators, maybe evaluator 1 and 2 are from the same department, and evaluator 3 is from a different department. It also matters what would be, for example, the total score you give in each category. Maybe teaching is evaluated fairly high and consistent, while in research there is more variance. So it's not a simple matter then of aggregating by averaging, and so we'll be discussing some methods that can also actually solve these kind of problems. The issue, of course, here is that we're not dealing with such a simple example, and in our cases, particularly for geographic information, we have to deal with spatial data. This could be 2D data if we're looking at surface, but in the surface it could be even 3D information. So the question is that we have many sources of information that could be potential of interest into what we're trying to study, and these could be of geochemical nature, geophysical nature, or say geological nature. And what we at the end want is probably a map that indicates some susceptibility or potential to presence or absence of a certain type of variable under study, which it could be mineral, geothermal, and landslides. So how do we combine all that information into a single map? So many of the methods that are available, and also the ones that we'll be discussing, are based for non-spatial data. And so in spatial data, of course, you have the issue of spatial correlation. And that's something we'll have to discuss, and something we'll carry down forward in the last part of the course, which is on geostatistics. So these are the 3 examples we'll be discussing: landslide, minerals, and geothermal. Minerals and geothermal are somewhat more similar in the sense that they are subsurface applications, where landslide are surface geomorphological features. Well, is it relevant? Well, if you live in California, as I do, it's been quite on the news. Here on the left-hand side, we see a picture of a landslide in Highway 1, the coastal highway, Pacific Coastal Highway, at Big Sur, which closed the highway down until further notice. I don't think it's even open yet. And even as we are sort of doing the course, this quarter we had a severe landslide in Los Angeles, which covered most of the 101 freeway, which is basically one of the major arteries going from northern to southern California. So in landslides susceptibility mapping, we have to clarify a bit of the nomenclature. So susceptibility is basically a likelihood of occurrence of a landslide, which can have a particular type and particular volume. So in that case, we're not talking about any kind of period, or specific period or area. When we deal with that, and we're looking now at the probability of occurrence, so it occurs or does not occur within a specific period, then we have a hazard. And so susceptibility doesn't include the triggering factors. So hazard would call in triggering factors, which are rainfall and earthquakes. Then we can use that hazard to calculate risk, which would be the expected loss in monetary value, because of course we don't know whether something occurs or doesn't. We only know a probability. And so a combination of how it would affect buildings and land use, then we can also calculate risk. So there are many approaches to doing that. There are the traditional physical approaches where we try to model the physical processes of landslides and slope stability. But of course, that requires physical understanding and modeling of the physical processes. And if we would apply that to real cases, then we'll have to measure the particular physical parameters that are involved in such physical processes, and they may themselves be subject to uncertainty. So the alternative approach would be to look at observations, do data scientific approaches, and allow yourself to incorporate a vast amount of empirical data. That is somewhat more difficult if you think about the physical approaches, of course, because it's very difficult to tune all these physical models to empirical data. And of course, we can also think about combination, and I think that's where people at this point are heading towards. Of course, landslide modeling and risk assessment itself is a huge field, just like say earthquake modeling and risk assessment, huge field of engineering. And so here I'll just provide a little overview just to give you an idea of where any kind of susceptibility or any kind of statistical modeling will take place. It will take place within a larger context, and it's actually important to understand this larger context because that would allow understanding what kind of things are important, such as what is really impact to total risk, and do some sensitivity analysis. I mentioned before that there are a number of factors that are involved. And so here at the top, we get a division of data. The box B is a hazard box, the C is a loss box, and that gets all calculated together into a risk box. So we have, of course, environmental factors, which are the ones that we will be looking at in this course: geological, morphological, geomorphological, tectonic, etc. Then we have land cover. We have triggering factors, which I said were earthquake data and weather data. And we also have a landslide inventory. And then there are the elements that are at risk: humans, buildings, etc. So some of these data are static. It means they're just there. You could also, of course, question whether morphology is static, but let's say we take that as not varying in time. And then there's other things that are varying in time, particularly weather, and to what extent that something is covered or not covered. And so we also have the observations that we actually are sort of using as a target, which is our landslide inventory. So all of that is then being used to go to the next box and do some kind of a magnitude frequency analysis. What magnitudes, what types of earthquakes are occurring with what frequencies, etc. This is very similar to the return level plots that we discussed in extreme value statistics. And so here extreme value statistics can be quite useful. The other box that I'm going to talk too much about in the end, so interesting to know what you'd like is if you're, for example, an insurance company in California would like to know this curve, which is how much loss will I make and at what particular probability does that occur. So in order to do all that, we'll have several data layers. data layers that are related to these various factors that I showed you before. And so when we talk about landslide susceptibility, we'll only be looking at environmental factors and the landslide inventory. So some of these data come from different sources. Some have different scales. Some are updated frequently or not frequently. All these things are not things we're going to discuss in this course. But typically, you could say for most of all this information, there is some field mapping, some field measurements, some laboratory measurements, and some remote sensing imagery. So when you talk about these kind of problems, there's a lot of bias problems. In landslides, for example, land cover is a big problem. Landslide may have occurred, but then say a number of years later, such as in the picture, that is no longer visible. So even though it's occurred, you don't measure it. There's also, in these data-driven approaches, particularly to landslide and also particularly minerals, there's a tendency to measure occurrence. We have a mineral deposit, but not no occurrence. It's rarely say that we drilled and say we abandoned the mine, there was nothing there. That's sort of something that doesn't happen. So these are kind of problems that are very common to this, and particularly later on in mineral and geothermal, we probably have very few observations of occurrence. And so that's then a problem in terms of tuning the statistical model. There are many methods used, and you'll see many things happening. If you read papers like this, there are statistical papers there. Then there's extreme value statistics. There's all kind of statistics that goes into that, and then many papers that are that deal with some of these or a variety or combination of these topics. So here's a simple, well, not a simple. Here's an example of how that would proceed. So here we're in the Himalayas. The climate is here pretty humid, so we have lots of rainfall, and so landslides are a big issue, and particularly when you have consecutive days of high precipitation. The data sets are quite substantial, and it's a well-studied area in that sense. So we have topographic maps, we have air satellite imaging, we have field studies mapping of different landslides, and inventory maps. So here's an example of landslide inventory as indicated, being of course dynamic per year as we observe more landslides. And so in that case, what you can see here what area we're looking at, how many landslides have occurred. You see in that period there's a large occurrence of landslides. Some kind of statistics about these landslides as well. What's also typical for landslides is that we don't just look at a landslide, but we look at various types. It could be rock slides, debris slides. They could be deep or shallow, and so people tend to make a distinction on that. So here's an example of an area, a geological map with landslides. So the colors here have to do with the lithology and the structures. And then here at the bottom, you can see that the various types of landslides that are occurring. And so this is over a certain period, namely this period here. So that is basically the red is basically the ground truthing, let's say, the target our Y value, predictor value that we'd like to look at. So what people typically use are topographic data, the slope and in the aspect based on DM information, lithology, the depth to bedrock, how much soil you have, of course. That will have to do with the depth of the landslide. The structural features, so being close to faults and major trusts is of course important if you deal with earthquakes. The land use and land cover, whether you're forested, of course, versus the forest is being removed, and other types of hydrological components such as streams and drains and so on. So then typically they would create these kind of maps of these various factors, and And of course, that itself, each maps by itself, could be a substantial amount of work, and that may involve interpolation, may involve geostatistics, may involve processing, may involve computer vision, etc. And the ultimate goal is to then, using all that information, to come up with a map like this, where you have areas such as here, where they have high susceptibility to landslides. So in combination with triggering factors that can be then combined into hazard maps, here low and high would be then purple. So mineral potential mapping is one application for spatial data aggregation when you deal with subsurface. So subsurface is more complicated. Obviously, it's very 3D. There are very few actual observations of deposits, simply because accessing those or mining those is, of course, a serious commitment. And also for minerals, we don't have as well developed physical models as for landslide, at least not to the extent that they're being used for making predictions. So here's an example of a mineral deposit in India. This is a base metal SEDEX deposit. And so here we see a geological map. Let me put on my pointer. Here we see a geological map with the various groups. And here, and as the triangles are basically the base metal deposits that have been discovered. So we notice here, at least for this particular example, we notice have already a reasonable amount of discovery. It would be more problematic, obviously, if you had only very few or just exploring the area. Then doing the analysis will be more difficult. So just a quick reminder, what is a SEDEX deposit? So it's a zinc lead deposit that is formed in a faulted sedimentary basin. Sometimes you'll see in the next slide, sometimes the host rocks are shales. And so what happens is that water recirculates in the subsurface, comes up via faulted structures, takes up the metals from the continental crust, and those then get deposited often on seafloor as what's called exhalative ore, and that's why we call it sedimentary exhalative deposits. So in terms of a genesis model, there are really sort of two cases. One is where the source is a sedimentary strata. So it's the sedimentary strata that carry those metal ions, they're trapped. Then during diagenesis, the pile dehydrates under heat and pressure and liberates those formations, those metals out of solution. The other one is where you have hydrothermal fluids. So those are generated in a magma chamber. And so this is typically associated with mid-oceanic rich environment. Of course, you have to have some kind of an active magma chamber. So you also notice then that, and this is important when we start thinking about susceptibility or potential mapping in this particular case, is that we need two things, which is transport of these brines. So we need the right stratigraphic pathways. So we need faults. And also we need trap sites. That means somewhere there needs to be, at least sort of, for example, on the ocean floor, there needs to be some kind of a depression. And so such that we can get a deposition of those dissolved metals. So this is also very similar, say, to a petroleum system modeling approach, where you need to have transport of petroleum, of oil, basically into traps. And so there you could say we have somewhat of a similar situation where we could look at various maps and various information and aggregate that together into a single map. So based on that information, we can start already to think about some recognition criteria. So obviously, well, in terms of big grouping, there's sort of stratigraphy, that's important, and then of course the heat generation and fluid center. So we need to have transport, which is the heat part, and we need to have a source, and then we need to have a trap. And that has to do with stratigraphy. So in that sense, we have to think about the host rock lithology. the stratigraphic position of particular important layering of particular important rocks, the particular sedimentary environment, and of course, because we're dealing with magnesium iron systems associated with mafic volcanic rocks, and of course the proximity to favorable structures as they have been observed. So here we see, first of all, a map of lithology. So this could be, for example, done by either geological mapping, as we'll see later, also in aggregation with geophysical data that has been carried out in this area. And we have a stratigraphic group. So this has to do with age relationships and which periods of the position that we have. Here are the predictor maps for the sedimentary environment, and in particular, we're looking at distance of coastline, for example, proximal shelf, distal shelf, deep water, etc. On the right-hand side, we have the mafic versus ultramafic rocks, and so they're also indicative of base metal deposits. Then we have geophysical data. So in this case, because we're dealing with mafic material, we're looking, of course, at magnetic field intensity data, so from which we can do a number of things. First, this data is often used to extract lineaments. That can be done with, say, computer vision programs that extract these linears here in the middle. They themselves could then, of course, be interesting in terms of their distance to these features may be important. And then, of course, you could just use the magnetic data itself to look at possibilities of mapping mafic magmatic rocks and their structures versus, say, background. So a fault itself is a thin feature, and the problem with that, including that into some kind of a predictor, becomes very difficult. So often what people do is they look at distances from faults. And so here are the primary faults, maybe secondary faulting, etc. These are basically various distance maps that you can calculate from the fault, the lineaments that are being discovered. So given the inventory that we have about existing deposits, we'd like then to calculate a map like this. The colors are a bit unfortunate. Red doesn't mean high favorability, means actually here low favorability. And so what we're interested in a map that says, well, here's high favorability. Where else would you then go look? Last example is geothermal energy, and this is relevant in many areas of the world. For example, in the United States, in the Basin Range province. So in 2005, the US GS was tasked to provide a national assessment of those resources that are capable of producing power, so within the United States. And that is indeed, of course, eventually for electrical power generation, or also for what's called enhanced geothermal systems. So there were already 250 identified geothermal systems, where in the assessment effort, of course, they'd like to possibly identify more and do that by incorporating more understanding about thermal, chemical, and mechanical processes that could determine or be an indicator of geothermal systems. So what do we need for that? Well, in the basin range particular geothermal system, we have magmatic activity. So we need, of course, we need heat flow in order to get hot fluids. We need faults within which that could be, those fluids can be transported. Seismicity can then, of course, be an indicator of such faults, and of course, stress is another interesting indicator, since it may indicate whether the faults are open or closed, so that the fluids could circulate, or at least the stress is aligned in a appropriate, or in a good fashion, let's say. So with that, the GeoSGS created several evidence layers. So here's the heat flow map. Now I have to sort of say, well, on the left here, let me put my pointer on. On the left here, we have the heat flow map. And so that heat flow map, of course, is not a true heat flow map. It's itself is is done by interpolations based on borehole data. So the indicator or the evidence map itself is can be, and as we see in previous example, is always a processed result. So here we see earthquake activity. We have stress measurements that then can be possibly integrated into the stress map. And then the target is to come up with a map like this, which is again the potential of having geothermal energy that then can be used for further identification of the amount of energy, say, that's available and how well it's available.